Hello, greetings of the day. My name is Prince Mehta, roll number 18BC120 from Institute of Technology Nirma University. Today we are going to discuss a topic called Quadtree. Let us first discuss about what the name suggests. So the name has the two parts, that is quad and the tree. Let's leave aside the quad and focus on the tree. So tree suggests that this particular thing or quad tree belongs to the tree data structure or the family of the tree data structure. So we all know that the tree has some root node or one root node, then some internal nodes and some leaf nodes. So the maximum allowed number of the children for an internal node decides the type of the tree. Okay, like if it's a binary tree, then in that particular tree at most two nodes will be allowed. Similarly, in the quad tree, the quad is the root of the quad comes from the Latin, which means that four or the fourth. So in quad tree, any internal node can have at most four children. Okay, so this was all about the tree representation. But what actually the quad tree does? So the quad tree will be given a 2D space, right, as input and some points. So it will divide your space according to the points on the particular space. And the order of that particular quad tree, it can be 4, 5, 6, any number. So if your order is 4, then in your particular one rectangle or in your particular one confined space, there will be at most 4 points. Okay. If there are more than 4 points, then it will be divided into 4 parts or the 4 quadrants. Similarly, it will divide recursively your that particular 4 parts or 4 children into further 4 parts if required. Or there are some variation or types of the quad tree that can be point based quad tree or point quad tree, then region quad tree, then point region, which is known as the PR quad tree, or polygonal map quad tree, or it can be compressed quad tree, and stuff like that. But we are not going into the depth of this all the types, but this all types are more or less similar to each other, right? And they are used according to its application. Let us enlist the applications of this particular quad tree. So it can be, the quad tree is mainly used with the image, like the manipulation of the image. So it will be like image compression or image processing or mesh generation or max disjoint dataset or state estimation, or if we go to the some basic application, it can be hit detection or nearest neighbor. And now let's have 2D space here. So this rectangle represents the 2D space, and now I'm adding some of the points in here. Let's take the round shape here, and let's say I have this one point, then this one point, it's way larger I guess, then further one point and another point. So here let's take the order as 3. So there will be at most 3 points in any region. So here we are having 4 points, 1, 2, 3 and 4. So this will be divided into 4 parts. So let's take let's divide it into 4. Sorry. Let's divide this space into 4 parts. Okay, so it's not necessary that all region will have equal number of points, like 1, 2, 3 and 4. Let's take one example in which this way is not happening. 1, then 2 and then 3. Here we are having 4 points, right? So this region should be divided into 4 parts. So let's divide this region into 4 parts according to our algorithm. So it's divided. Now, as we have discussed that this region does not contain any points, so it will not be assigned any object, or any object will not be created for this particular region or the quadrant. Similarly for this 3. But this particular region has 4 points, so it will be assigned object. And we know that recursively the quadtree algorithm will be applied for all of them, the region. So it will be again applied to this one and further divided into parts because it contains more than 3 points in one region. Now it's fine, because this first region has 2 points, this has none, this has none, this again has 2 points. So the property is satisfied. Now if again I add 1 point here, 1 point here, this again it will be divided into 4 parts, and it will check whether there are any region whether there are more than 3 points or not, and so on. It will recursively do this thing. Now this visualization is developed by the jimgang.com. We are using this for the educational purpose. Okay, so the root node will represent or points towards the whole 2D space, right? So this is the whole 2D space. Then its roots, its four roots will represent the one of the quadrant. So this will represent the fourth quadrant. Similarly, this will represent the second quadrant, and the other two will represent the other two quadrants. So this was the corresponding between the 2D space and the tree. As we have seen in the BST binary search tree, the search time is the logarithmic in general case. But so in our Quadtree as well, the search time or insertion time for both the functions, it will be logarithmic for base 4. Now, if I want to find out this particular node, then I have to go through the 1, 2, then 3, 4, 4, 5, and 6 and 7. So 1, 2, 3, 4, 5, and 6. Okay, I have to traverse through the 6 nodes, and I will get this particular point. But what if I'm having a worst case scenario where my all the points are confined in the only the in the one portion only? Let's say this is my 2D space, and my all points resides here. These are the 4 points, so it will be divided into this manner. So initially, if we can say here that this quadrant, and this quadrant is empty. Now, again, this has the 4 points, so it will be further divided into 4 parts. Again, these 3 quadrants are empty. Again, this is having the 4 parts, so it will be divided into further. Now it does not have any points, so it's fine. But what if I add again all the points in this portion only? So in this way, the tree will be most of the nodes will contain nothing. So they will be just empty shell or the empty buckets. So this kind of structure will create a tailed tree that will be like this, then other, then this one, then this one, and this one. And if I show some, there will be other 3 quadrants, but they will not contain any information. So now if I am having another point in the same region, which is here, so I have to traverse through the whole tree. So the time complexity for this adding insertion will become big of n. And even if I want to search for this particular node, then also I have to traverse through the whole tree. So it will be of big of n. So the average is big of log n, and worst is big of n. Let us check the application of the Quadtree. And the problem says that you will be given a point, right? And we are supposed to find out or figure out that that particular point belongs to our space or not. So if we go with a naive approach, then it can be we can compare that particular given point with our all the points we are having in our space, right? But it will take big O of n time. Like if we are having let's say 1 million dots or 1 million points, then we have to compare for the 1 million times, right? And the other approach can be so this is not the time efficient, but the other approach can be that we will make a boolean 2D array, and wherever we have a point, we can make it true, otherwise it's false. So let's say if we are given a point like 5,4, then we will check that is it a point where 4,5? If it's true, then yes, and if it's false, then no. So this is time efficient, but the space complexity will be very large for this particular thing. Like it will totally depend on the maximum or the range of the particular coordinates. Like what will be the range of the coordinates 0 to 600 or 0 to 700 or stuff like that. So it will take n cross n, and we generally don't have any bound on the coordinate size. So here our Quadtree helps us. Like if I want to find out that is there any point belongs or do we have any point or not, so it will very reduce. Like if I want to check that this particular point belongs here or not, so let's see how many comparisons we have to make for this particular thing. So first we will check in the particular whole bunch thing. Then we will go for the 4th quadrant as its range. Then we will go for the 1st quadrant, and then we will go for the node. So 1, 2, 3, and 4 comparisons only to find out that do we have a particular point or not. And if we lead to a node or a leaf where we do not find out our particular point, then we do not have a point. The answer will be no. So it's very time efficient as well as the space complexity wise efficient algorithm. So it will work in the big of log n time. So this is the second application or second basic application of the Quadtree. In this problem, we are supposed to find the nearest neighbor of the given point. So as the input, we will be given x coordinate and y coordinate for the particular point. Now, in this visualization is taken from the it is built by Patrick Surrey, and we are using it for the educational purpose. So whenever I put a particular point, there are a few things that one should notice here. That is, the shade of the green color, and the color of the dots. There are black, orange, red, and yellow. So let's first discuss about the shade of the green color. So the green color, the darker the green color, it shows that it is how many times visited. So the light green shows that it is visited less than this dark green portion. Okay. Now and the okay, we are using the Euclidean distance formula to find the distance between the points. So if we are applying the naive approach, then we have to apply n times Euclidean formula to compare our point with each other point. But let's say I am having this particular 2 points, like yellow and the this yellow and this particular point. So the distance between these 2 points and the distance between this yellow and this particular black point, it will be obviously larger than these 2 points, right? It will be larger than these 2 points. So there is no meaning of finding this Euclidean distance. So in that way we are eliminating. Now let's say I want to find distance between this point, this yellow point, the nearest neighbor. So it will search for in the whole space, then it will eliminate this 2 quadrants, then it will eliminate this quadrant, then this quadrant, then it will check for this quadrant, and then after some saturation distance it will apply the Euclidean distance for some of the selected points. And so some of the selected points are these orange points. So it has applied Euclidean distance formula for only for 5 points, and the red one is selected as the nearest neighbor. We wanted to find all the hotels in a particular area. So let's say this square, or this square is our city, okay, and I wanted to find the hotels in this particular area, right, this rectangle. So how can I do that? This way. So these 1, 2, 3, 4, and 5 will be detected as the hotels in our area. So in that way we can find a particular object in particular area. The other application that is possible for the nearest neighbor, that can be that suppose we can use this in the car services like Uber or other like that. So I am at this place. So I can find out, or the Uber application can suggest me that these are the Uber cars near you. So you can catch any of them. Similarly, it is useful for the drivers as well, that which are the customers near in the some particular area. It can be 2 kilometer or 3 kilometer. So in that way, this Quadtree is useful in real life applications. Okay, now let's discuss the advantages and disadvantages of the Quadtree. One of the main advantage of the Quadtree is that the image can be represented compactly in the form of the Quadtree. You can do all kind of manipulation like compression and changing the color from black and white to some color and stuff like that. Or we can compare two Quadtrees as well. If in that manner we can compare two images as well. The other application or the other advantage is that we can rotate any image by 90 degrees very easily. So if we are representing our quadrants by north is south, is southwest, and northwest, then if we want to rotate it by 90 degrees, then all we have to do is that we have to shift all the things. If we are doing clockwise, then this will happen, that northeast will become at the place of the southeast, southeast at the southwest, southwest we go to northwest, and northwest will go to northeast. So in that manner this is rotated by 90 degrees. Now let's come out for the disadvantage. One of the disadvantages is that it can rotate image by 90 degrees only, or in the multiple of the 90 degrees, like 90, 180, or 360, or 270. So we cannot rotate it by 30 degrees. So another thing is that suppose we are having an image and we have its Quadtree representation. Now we rotate that image by some degree, say 30 or 40 degrees, and again we generate a Quadtree. Then the Quadtree before the rotation, the Quadtree after the rotation, there will be a drastic change in both of them. We cannot compare anyhow, or we cannot find the degree of the change in both of the trees. So because of this limitation, the Quadtree cannot be implemented or cannot be used for the visualization or shape analysis or pattern matching and applications like that. But still, the Quadtree has many applications in the image processing. It can be used in the 2D space, and if we are in 2D games, if we are talking about the 3D game, then the variant of the Quadtree, which is known as the Octree, OC, it can be used for the 3D space in graphics as well.